Now let us work on new dataset. This dataset has 6 variables: bio, geo, chem, algebra, calculus, statistics, and some 300 records. I have already saved this data at CSV and I'm going to read this data in R. So by that time, let me clean up my space so that everything looks clear. So here is let me first read the data set. So I got the data, all 6 variables and 300 rows, which you can see here. Let's check the correlation. So I have got the correlation here. I'm going to put it on PPT, so that I can show you without going to and fro. So let me first show you the PPT, that how does the correlation looks like. So the same correlation that you have seen here, only thing is that I have slightly truncated the decimal places so that I can show it to you a little comfortably here. So take a look. You know, it is bound to happen that the correlation that you have between geo and bio is same as bio and geo, and that's why if you look at half triangle is as good as seeing the full thing, because whatever you are seeing between calculus and bio, same has to happen between calculus, bio and calculus, 0.21. So it's just the mirror image. That's why we can focus on just one part and still can make sense of this. Now let's understand one thing. Which are the variable which appears correlated to you? You can pause the video and think of. If you think of bio and geo appears having good correlation, and as well as bio and chem. Similarly, chem and chemistry and geography appears little correlated. If you look at these 3 variables appears to have quite low correlation among any of the 3. However, if you look at between algebra and calculus, there looks a good correlation. Same way, calculus and stats has lower correlation, but still it is little sizable than others. So if you look at by natural look itself, it appears that there is little groups in the variable. Probably these 3 variables are behaving in a similar way and these 3 variables. Now let's go ahead and run the factor analysis in R. So what we are going to do, very much the same way which we had done last time. Take a look. This is very small number, so this is highly significant. It means one variable, one factor is not at all sufficient. Let's take a look at 2 factors. 2 factors is giving you p-value 0.568, which is obviously not significant. It means these 2 factors are sufficient to explain the model. If you try with 3 variables, just see what happens. You see all of a sudden the freedom is 0, so it is giving some strange stuff. I should say like we'll remain focused till factor equal to 2. So now let's once again run for factor equal to 2 and take a look at the different statistics. So here we had found that p-value is insignificant, so we are quite okay with this model. And we also realize that there is no point adding another factor here. Now what we will do, we'll go each and every part of the output. But first let's go to this portion and then I am going to explain you this uniqueness. So first portion is actually uniqueness, but I am going to first explain you this portion. So let's take a look. What is this portion? So this is how the loading of the factors has come up. So if you look at the way it appears in R, that factor 1 has huge loading of these 3 variables, bio, geo, chem, and factor 2 has huge loading of these three variables: algebra, calculus and stats. What is this? It is the correlation of variable with the factor. So what is the correlation of biology with factor 1? What is the correlation of biology with factor 2? The square of this will explain you the coefficient of determination, means the square factor loading is the percent of variance in the independent variable which is getting explained by the factor. So if you ask me what percentage of biology variance is getting explained by factor 1, is 0.86 into square, 0.686 square. So if you ask me anything which is greater than 0.7, that's a rule of thumb, means that variable is getting pretty well explained by the factor. And why I'm saying that? Because if you think of any coefficient of correlation 0.7, the square of that means 0.49. So if anything is greater than 0.7, it means roughly at least 50% of the variance of that particular variable is getting explained by the factor. Now what of the total? So look at, let's also understand one point. Is it same as what we were getting in principal component analysis? The best would be that we take a look, we run the principal component analysis and take a look again. So let's just run on the same data the principal component analysis. And let's take a look at the loadings. So if you look at, it says minus 0.494, minus 0.486, all those things. So this is pretty different from what loading you are getting in case of factor analysis. What you need to understand, the loading in both the cases has different meaning. Here it is telling you that how you can combine biology, geology, chemistry, algebra, calculus and stats, the standardized value of these variables to get the component 1. If you recall, minus 0.494 into bio standardized, minus 486 into geo standardized, all those things will give you component 1. Whereas in this case, in case of factor analysis, it is nothing but the coefficient of correlation. So coming back to that, it is pretty clear it is different. There it was how to construct PCH from variables, here it is coefficient of correlation. Will these two factors explain all the variance of all the variables? Actually not. Let's take a look. It is getting explained partially. So what percentage of biology variance is getting explained by factor 1 and factor 2 together? It will be given by factor 1 will explain 0.86 square, factor 2 will explain 0.13 square, factor 1 and factor 2 taken together will explain 0.86 square plus 0.13 square, 0.748. That's what is getting explained by factor 1 and factor 2. So what percentage of biology variance remains unexplained by factor 1 and factor 2? That is 1 minus 0.748. And if you look at, that is the uniqueness of biology variable which is not getting explained by factor 1 and factor 2. And that's what R produces. If you look at the first thing that it says, uniqueness, biology 0.252, which is very much what you are seeing here, that's how it has got explained. So factor 1, if you're taking just factor 1 and factor 2, 25% of variance of biology is still unexplained. Similarly, we can calculate uniqueness of other variables. What is communality? Communality. Communality is what percentage of variance is getting explained by factor 1 and factor 2. It is actually nothing but 1 minus uniqueness, or otherwise uniqueness is equal to 1 minus communality. So if you ask me what is the communality of biology, it is 748. So factor 1 and factor 2 together has 0.748 common stuff between bio and factor 1 and factor 2. Now the last step. Can you name factor 1 and factor 2? If you look at this, is in some sense it's giving you scientific aptitude, and this is in some sense is giving you mathematical aptitude. That's how you do it. So let's take a look at our output once again. We understood uniqueness, we understood loading, we have also understood how to interpret this, and only when it is insignificant we started delving into the detail of that. Now let me explain you what does it mean. This tells you that out of total, if each and every variables you are taking, this is like the square sum of loading. So if you look at this, factor is explaining 2.12 and this is explaining 1.863. It is very similar to that if you take all standard variables, the variance of the total data will become 6, and that's why 2.124 divided by 6 will give you that this factor is explaining 35.4% of the total variance, and 1.863 divided by 6 will give you 0.311. Factor 1 and factor 2 taken together will explain 0.354 plus 0.311, 0.665% of the total variance. Means 66.5% of the total variance in the data is getting explained by these two factors.